Dr.N.Uma Associate Professor in the Department of Chemistry, the Standard Fireworks Rajaratnam College for Women, Sivakasi. Welcome to the module on atomic structure and electronic configuration. Dear learners, today we are going to look into the atomic structure and its evaluation and the filling up of orbitals, what is known as electronic configuration. Atomic structure refers to the structure of an atom comprising a nucleus at its center, in which the protons, which are positively charged, and neutrons, neutrally charged, are present. The negatively charged particles are called electrons and they revolve around the center of the nucleus. The various atomic models developed will be seen here afterwards in the forthcoming slides. The first theory was proposed by Dalton. Dalton's atomic theory says that every matter is made up of atoms and atoms are indivisible. Specific elements have only one type of an atom in them. Each atom has its constant mass that varies from element to element. Atoms undergo rearrangement during the chemical reaction. Atoms can neither be created nor be destroyed, but can be transformed from one form to another form. The demerits of Dalton's atomic theory goes like: the theory was unable to explain the existence of isotopes, nothing about the structure of atom was appropriately explained, and later scientists discovered particles inside the atom that proved the atoms are divisible. Next comes Thomson's atomic model. It is based on the cathode ray experiment conducted by Thomson. It is commonly called plum pudding model because it can be visualized as a plum pudding dish where the pudding describes the positively charged atom and the plum pieces describe the electrons. Thomson's atomic structure described the atom as an electrically neutral, that is, the positive and the negative charges were of equal magnitude. But in this model also we have certain limitations. Thomson's atomic model does not clearly explain the stability of an atom. Also, further discoveries of other subatomic model other subatomic particles couldn't be placed inside his atomic model. So, the next comes Rutherford's structure of atom model. From the alpha ray scattering experiment, Rutherford explained that the nucleus is at the center of an atom, where most of the charges and the mass is concentrated. The atomic structure is spherical. The electrons revolve around the nucleus in a circular orbit, similar the way the planets orbit around the sun. What are the limitations? If the electrons have to revolve around the nucleus, they will spend energy, and that too against the strong force of attraction from the nucleus. The electrons will spend a lot of energy and eventually they will lose all their energy and will lie into the nucleus. So, the stability of the atom is not explained well by the Rutherford atomic model. If the electrons they continuously revolve around the nucleus, the type of spectrum expected to be is continuous. But in reality, what we see is a line spectrum. So next comes Bohr's atomic theory. The electrons inside atoms are placed in discrete orbits called the stationary orbits. The energy levels of these shells can be represented via quantum numbers. Electrons can jump from higher energy levels electrons can jump from the lower energy levels to higher energy levels by absorbing energy and move to lower energy levels by losing or emitting their energy. As long as the electrons stays in own stationary, there will be no absorption or no emission of energy. Electrons revolve around the nucleus in these stationary orbits only. The energy of the stationary orbits are quantized. What are the limitations of Bohr atomic theory? Though it explains well about the moving or jumping of the electrons from one level to another level, we can see that the Bohr's atomic structure works only for single electron species such as hydrogen, helium and lithium 2 plus or beryllium 3 plus ions. When the emission of spectrum of hydrogen was observed under more accurate spectrometer, each line spectrum was seen to be a combination of many smaller discrete lines. Both Stark and Siemens effect couldn't be explained using such Bohr's theory. So here comes the pictorial representation of an atom and its shells. The left hand figure showing alternate colors with circles, then atom model. At the center, P plus N tell you the number of protons and neutrons. Also, the increasing number N with 1, 2, 3, 4, 5 represents the values of the principal quantum number, which will also equal to the number of shells which are present according to their energy level from the nucleus and represented as K, L, M, N and O. And below the nucleus we have E is equal to 2 for the K level, E is equal to 8, that means the maximum number of electrons that can be accommodated in each shell is represented down. So, E is equal to 2 for a K level and for a N level where we could have the principal quantum number as N is equal to 4, we could accommodate totally of 32 electrons in the N level. Okay. So, the formula to obtain the maximum number of electrons that could be accommodated in these main energy levels of an atom is 2n square, where n represents the principal quantum number, or in terms we could say the shell number. And then when you look at the 4 different quantum numbers which is represented below this diagram, first one, the main energy levels are described on the basis of the principal quantum number, then the subshells are represented as the azimuthal quantum number, then their orbitals are represented with the magnetic quantum number, then according to the spin quantum number only we can accommodate the clockwise electron as well as the anti-clockwise electron in an orbital. So, this diagram represents the various evolution period and the models of atom. Next, we will get into the electronic configuration of atom. Electron configuration of an atom describes how the electrons are distributed in the atomic orbitals. Electron configuration of an atom follow a standard notation in which all the electron containing subshells are placed in a sequence. For example, the electron configuration of sodium is 1s2, 2s2, 2p6, 3s1. There are 3 important rules, namely the alpha principle, Pauli's exclusion principle and Hund's rule of maximum multiplicity. The 3 rules govern the arrangement of electrons in various shells, subshells and orbitals. First, we will look into the alpha principle. Alpha principle is based on the word of being, which means built up. According to alpha principle, electrons occupy the orbitals of lowest energy first and then moves to the higher energy shells. In the Afar diagram below, each box represents an atomic orbital. So, we got all the yellow color circles represented as 1s, 2s, 3s, all the s orbitals in the sequence, and the blue color circles, they represents the b orbital, and the pink color represents d and the green color represents the f orbitals. So, when we have the principal quantum number n as equal to 1, the main shell, that is the K shell, will have only one orbital which is represented as 1s. For s orbital, the azimuthal quantum number value is equal to 0. Then when the value of n is equal to 2, then the L main shell will have 2 subshells, and out of the 2 subshells, there are 1 s orbital and 3 p orbitals. These 3 p orbitals, p are named as px, py and pez according to the magnetic quantum number, and s orbital will have the azimuthal quantum number as explained earlier equal to L is equal to 0, and the p orbital will have the azimuthal quantum number value as equal to 1. Similarly, when you go for n is equal to 4, the level will have 4 orbitals. When we go for n is equal to 4, the level, main energy level will have 4 subshells, one s orbital, p orbital, d orbital and f orbital. Raja, idu romba cut pananum. When n is equal to 4, we will have 4 subshells, s subshell, p subshell, d subshell and f subshell. And we know according to the magnetic quantum number, s will be the single orbital, but p will have 3 orbitals, d will have 5 orbital and f will have 7 orbital. So, according to the Afar principle, once if you have 3 electrons, according to the system, first 2 electrons will go to 1s orbital and the third electron will go to 2s orbital. That was shown very clearly by the red headed arrow marks. Writing the electronic configuration of sulfur according to Afar principle explores the usage of Afar principle very clearly. The atomic number of sulfur is 16, so implying that it holds a total of 16 electrons in it. As per Afar principle, 2 of these electrons are present in one subshell, 8 of the electrons are present in 2s and 2p subshell, and the remaining are distributed into 3s orbital and 3p orbitals. Therefore, the electronic configuration of sulfur could be written as 1s2, 2s2, 2p6, 3s2 and 3p4. There are certain exceptions. Let us look into the electronic configuration of chromium. The electronic configuration of chromium is argon as the inner core, and the valence core will contain 3d 5 electrons and 4s 1 electron, and it should not be like argon as inner core with 3d 4 and 4s2 as suggested by Afar principle. The exemption is attributed to several factors such as the increased stability provided by the half-filled subshells and the relatively low energy gap between the 3d and the 4s subshells. The second rule to be followed in writing the electronic configuration is Pauli's exclusion principle. Pauli's exclusion principle states that maximum of 2 electrons, each having opposite spins, can fit in an orbital. This principle can also be stated no 2 electrons in the same atom can have the same values for all the 4 quantum numbers. Therefore, if the principal, azimuthal and magnetic quantum numbers are the same, the 4th quantum number, that is the spin quantum number, must be different. That means they should have opposite spins. The electrons should have opposite spins. That was very clearly explained in the diagram given below. For Pauli's principle, see For the 1s orbital we have 2 electrons and also the 2s orbital have 2 electrons and they are having opposite spins. That means the spin quantum number for the first 2 electrons in the 1s orbitals are respectively plus half and minus half. The same is the case for the 2s electrons. The third important rule is the Hund's rule of maximum multiplicity. This rule describes the order in which the electrons are filled in all the orbitals belonging to a subshell. It states that every orbital in a given subshell is singly occupied by the electrons before a second electron is filled in the orbital. In order to maximize the total spin, the electrons in the orbitals that only contain one electron all have the same spin. Say for example, in this case, the diagram given below describes the electronic configuration with 6 electrons. So, according to the concept, what we have to do for the filling up of electrons with p orbital, we can see. So, out of the 6 electrons, as per the Affa principle and the Pauling's principle, we could fill the 1s orbital and 2s orbital with no confusion. But when we have to fill the remaining 2 electrons in the 2p orbital, we have to follow Hund's rule. We couldn't put all the 2 electrons in the same orbital as shown on the right side. That is an incorrect electronic configuration. So, we have to follow Hund's rule of maximum multiplicity. When we could have the maximum multiplicity? When the electrons are filled with odd number. Each orbital is filled with odd number of electrons, the number of multiplicity will increase. So, the configuration what is written on the right hand side is the correct electronic configuration. So, this shows very clearly the electronic configurations of some of the selected elements. Say for example, we can take the electronic configuration of nitrogen as explained just now. We can have the filling up of the px, py and pz orbital according to Hund's rule with single electron in each of these orbitals. Let us take another example of electronic configuration of oxygen. Oxygen atomic number is 8. So, we have to fill up 8 electrons in the available orbitals. So, first orbital, the 1s orbital will be filled with 2 electrons. Similarly, the 2s orbital could also be filled with the 2 electrons. So, after filling these 4 electrons, the remaining 4 electron has to be filled in the 2p orbital. So, we have 2px, 2py and 2pz orbitals. Out of these 3 orbitals, first we have to fill up each orbital with 1 electron. So, 3 electron will be filled. Px with 1 orbital, 1 electron, py with 1 electron and pz with 1 electron. The 4th electron will go to the 2px orbital and get paired up. So, totally the 2p orbital will have 4 electrons. With the base of these electronic configuration, we can classify all the available elements in the periodic table as S block elements, P block elements, D block elements and F block elements. Let us look into these elements and their properties in the next coming modules. Thank you for your learning.